We are live, ladies and gentlemen, or at least YouTube seems to think we are. Oh, right. Interesting. Hello everyone. Welcome to the irregularly scheduled programming streams where we write code on stream. So as I'm working on the meshoptimizer, I was finishing some things that I was doing for GLTF format, and they work pretty well in the web context. And then I decided, well, let me check if they work reasonably well in the native context. And I have these three functions really, or it's either 3 or 4 functions depending on how you count, that perform relatively straightforward transformations on the data. And we can run these transformations using scalar code that I wrote at some point. So it's, there's like a page and a half, I guess, of scalar code across these 3 functions. Or you can run them in SIMD, and for SIMD, I converted them to SIMD using WebAssembly SIMD. And I was getting pretty good performance with this, so we are looking at this section where we just take large buffers of data and transform them with these functions. And I'll go over what the functions do in a second, because I actually need to document this. So we're getting reasonably good results, right? We're getting between like 2 to 12 gigabytes per second, as it were. And this is running in WebAssembly SIMD, so there's some amount of time being lost on various impedance mismatches between the WebAssembly spec and what x64 or like SSE2 can do. And then I decided to run this in native code, where I can do this, where I'm just gonna compile this with GCC. I should probably remove the FOpenMP stuff, but like whatever. And so this is the scalar code, right? And as you can see, the scalar code performs substantially worse. So this is like 0.4, 0.8, 0.8 gigabytes a second, where this is 8 times faster or so. Can I multiply? It's not quite 8, it's like 5 times, whatever. So substantially faster, except for this last one where it runs at around the same performance, around 12 gigabytes a second. And so what it boils down to is that in the last example, the compiler actually vectorizes the code. I think if I use Clang, it actually doesn't do that. Let's see. Yeah, so if I use Clang, then this actually runs a bit better, but this is scalar code still. This runs considerably worse, and I think the reason is because Clang doesn't vectorize this, right? You can use, so the reason why, like I added an OpenMP flag so that I can try to say, hey, maybe the compiler technology is like 2020, right? These loops go over the data, and each object, each like item, is transformed in a way that doesn't depend on any other elements. So in theory, all of this should be vectorizable, and my vectorized code for WebAssembly isn't too crazy. And so I was thinking, well, surely I can maybe tell the compiler, hey, like it's really important. And then if you run this with Clang, then Clang says, well, your loop that you asked me to vectorize isn't vectorized. Oh, one thing I haven't tried actually is, does Clang do unrolling now? How does this work? Does it work like this? Let me remove this. I'm not completely confident. Clang now has a loop unroll attribute, though. Interesting. Okay, yeah, Clang now has a loop unroll attribute, but I guess it doesn't do anything in this case. Maybe it already unrolls this loop. Yeah, whatever. Point being, the magical technology of auto-vectorization is still not there. So what we have to do is we have to just manually vectorize these functions. And so in addition to manually vectorizing these functions, we need to document these functions. And the reason why we need to document these functions is that I'm writing the spec for the GLTF extension. And the spec is supposed to say, hey, here's what the bits of the data, here's how the bits of the data are stored in the GLTF file, and here's how they are interpreted. And this code is kind of part of this, so I have to document this as well. So I figured I might as well do both of these at the same time, and then might as well do both of these on stream, because why not? You know, for people who are stuck at home, which is everybody right now, maybe you'll have fun watching this, or maybe not. It's kind of up to you. I'm just gonna go. I'll pay a little bit of mind to the chat just in case people have questions as we go. But in general, the goal is to document these transforms. So there's 3 of them. There's the octahedral transform that's used for normals, quaternion transform that's used for quaternions, and exponential, which is used for general floating point data. The octahedral transform actually has 2 variants, the 8-bit and 16-bit, and so in C++ land and scalar code I just have like one function, but when I was doing the WebAssembly SIMD conversion I had to do 2 functions. And our process will be, we'll take the WebAssembly code, because that's already running in SIMD, that's already reasonably fast, we'll mechanically convert it using just like intrinsics to the SSE version, and then we will try to see if we can make the performance better. Because we know a bit more about the... oh, this is interesting. We have access to basically all intrinsics that we could need, right? So we know a bit more about the target architecture, so we should be able... oh, and we have a stronger code generator, Clang or GCC, so we should be able to get faster on WebAssembly SIMD, presumably, as a result. It's been a bit of time since I wrote this code. I remember roughly what decisions I was making, but not fully. And we will start perhaps, so we have three or four functions to convert. We'll start with the last one, this exponent one, because it's the simplest one, and this is just to get us going. Like right now the compiler already vectorizes, not the Clang compiler, but the GCC compiler. Oh, wait. Already vectorizes the, oh god, hold on. I have to fix my build system setup whenever I switch compilers. I don't switch the target kind of object output, so things don't work super well. Anyway, so GCC already vectorizes this last function, right? But for one, Clang doesn't, unless you tell it to. And I'm not actually sure what Microsoft Visual Studio does with this code. I guess we could check, but I'm kind of too lazy to do that. Or actually, you know, let's just do... let's quickly check what Visual Studio does with this code. Just, you know, just out of curiosity. Alright, so... why? Oh, this is glorious. The command completion doesn't work with this slash, I guess. Yeah, okay, great. Let me know if the fonts are too small or too big or whatever, and I will figure that out. I guess I don't need arc. Maybe I need FP fast. Oh, I'm not actually using fast math in my GCC or Clang builds. I should try to do this. Maybe the vectorizer behaves better. Okay. All right, so this doesn't look vectorized at all to me. Let's see. The code is faster than it was with GCC or Clang. However, I am using FastMath, so maybe that has something to do with that. It's kind of interesting that even here it's faster. Microsoft's optimizer is getting better and better these days, so it's kind of refreshing to see. Let's see if I need anything possibly to enable auto-vectorization. I thought it's enabled more or less by default. Oh, maybe not. QPAR. All right. Let's see. Nah. Maybe like it vectorizes something, but does it so poorly that it doesn't. It's not actually very fast. But anyway, so like right point being, the compilers don't really vectorize this code. Microsoft's compiler doesn't. Clang or GCC don't really. We can try to enable fast math, but the odds of that, maybe this changes something. So let's just do a final control check. Maybe with fast math, GCC or Clang vectorize some of these functions. Nope. Well, the last one is, but the last one wasn't before fast math. And Clang. Oh, maybe I'm. No, I'm using O3. Yeah, no. So, might as well basically do this ourselves. The last function, the simpler function, is vectorized by GCC, but not Clang or Microsoft Visual Studio, and everything else just isn't vectorized. So let's do this, and as we do this, we will document the function in terms of what behavior it has, and then we will actually optimize this. So the point of all of these filters is to improve the, not necessarily improve, like to give a way to trade off quality for, or precision for size. So this function, using this function, you can encode a set of floating point values with less precision that you normally get out of floating point values, and all of the encodings are tuned very specifically to be compatible with some other compression algorithms that meshoptimizer implements. So let's just start going through that, and we'll start with exponential, and maybe we'll just go like in kind of do this first and then do this one, and then do this one. We'll see. So the idea in this exponential filter is very, very simple. Let me try to... so since I'm gonna be writing the specification as we go, wait a second, let me... Cool. I wanted to leave a note to the effect of like for performance reasons, the results of the decoding process are specified to 1 unit in last place in terms of or relative to or the decoded data. For example, if a filter results in a 16-bit integer, decoding may give to 1 in a 16-bit normalized integer. Decoding may produce results up to within of specified I don't know if this is really important at all, but definitely maybe it'll turn out to be a bad idea in the future and we'll have to specify things precisely, but it's definitely the case that in some of these functions you may consider, it's like, oh, I have this really neat trick that could save me like 10% of the time, but could cause some precision loss in the output value. And maybe it's a reasonable trade-off, because the whole point of all of these functions is to provide some way to trade off precision for size. Having said this, the implementations that I have so far, I think they're a bit exact for all like reasonable, for values with reasonable range. So I don't even know if this is particularly important, but there we go. So the exponential filter. So the exponential filter is really, really simple. So the way the floating point values are usually stored is one sign bit, and then 8 exponent bits, and then many mantissa bits, like whatever, 23 mantissa bits. And mantissas usually, unless like the exponent is 0, have an implied 1 bit in the beginning. So really we are talking about a value like this, and then the resulting floating point value is s times 2 to the power of e times 1 fraction, right? Where sign is plus or minus 1, and also the exponent is biased, but it doesn't really matter. So the reason why this is not great is twofold. One, let's say you don't want 23 bits of precision in your mantissa. You can reduce the mantissa precision by, say, replacing the last bits with 0. So you could do something like this, right? Turns out it's not always great for my encoder, for the encoder that kind of encodes all of these values. Like you can like add zeros to the end, but it's not the best idea. The better idea is to add zeros to the beginning. So that's not always great. The other thing that's not great is that the first byte, so all of this, the point of this filters is to improve the compression ratio for the data by the codec that gets run after this, and that codec works with bytes. And so here the exponent isn't in a byte. There's like 7 bits of the exponent in 1 byte and 1 bit in some other byte. And this causes other inefficiencies. So what I decided to do is to make a format that I'm sure there's like a name for this format, because the idea isn't particularly unique or smart. But instead of doing this, I decided to store values like this. It's 2 to the power of e times m, where m is a signed 24-bit integer. That's it. When I say signed 24-bit, I mean there's like 1 bit for the sign and 23 bits for the value, but unlike the floating point mantissa encoding, 1 is not implied. So for example, you could say, well, m is -1, and you have 2 to the power of 0 times -1. You could say something like 2 to the power of -1 times -2, right? And that's the same value. So there's a bit of redundancy in the encoding because 1 is not implied, but this allows you more freedom when you're choosing the exponent, because effectively you could say, well, I kind of want the exponent to be 5. Just, you know, just like I did, well, 5 is a bad value. Let's say you can decide the exponent should be -5 in all of the values that you encode. So you always encode something like 2 to the power of -5 times m. This means that you have a finite precision if you chose the exponent to be -5, but your exponent is always the same value, which means it compresses really well. And so choosing this representation means that the encoder gets freedom to pick the exponent that's the best balance in terms of precision versus quality. You do lose a bit out of this because the 1 in the mantissa is like the leading 1 bit has to be specified, but you know, it's fine. So how do we specify this now? how do you specify this? Allows to include floating point values with a range close to the full range of a particular floating point value, but allows more control over the exponent mantissa to trade quality for precision, and has a bit structure that is more optimally aligned to the byte boundary and to the strengths of the vertex codec, but whatever. The input to the filter is a sequence of 32-bit integers. Oh, right. Okay. 32-bit little endian integers, I guess, with the top bit, top 8, most significant 8 bits, specifying a signed exponent value, and the remaining 24 bits specifying a signed mantissa value. The integers are stored in two-complement format. The result of the filter is 2 to the power of e times m. For optimal. So when you have something like this, when you have like this integer, right, that's just encoded, maybe I should specify this somehow. I don't know how formal the specs should be, so for now, or maybe I can do something like this, where I have the text representation of this, and then I just say something like exponent is the input shifted by 24, given a 32-bit integer input. Something like this. Should it be just pseudocode? I don't know. But okay, so we decode the exponent and then we decode the mantissa. So to decode the mantissa, you have to take the last 24 bits of the input, but then you have to sign extend. And it's gonna be awkward to, you know, whatever. And then we're gonna return power of 2e times m. All right. So who knows if, you know, who knows if the spec should be written this way, but it doesn't really matter. So the decoding function, as I wrote it, you could implement this as is, but the problem is the power function isn't very cheap to compute, so we have to cheat a bit, which means that we have to compute the power of 2 by just using bit manipulation on the floating point value. And so to do this, though, the thing is, in floating point numbers, the exponent that is kind of stored in the floating point bits is slightly different from my exponent here. So for example, what's a good example? Or actually, is this fine? Hold on. It's kind of the same exponent. But I was going to say that something like the valid range of exponent is I wanted a slightly smaller range than the one that's allowed by the format, which is 127, 128, because like I'm not sure what the exact boundary conditions are. Like probably if the exponent is I think if the exponent is like minus 127 exactly, then this is a special value in floating point terms. And so I wanted a slightly smaller range. And I'm not sure what exactly that range should be. I kind of was thinking, you know, which facilitates, I don't know, performant implementations. But also, if you really need, as part of GLTF file, if you really need to encode something like 2 to the power of 100, you're probably making a mistake somewhere. All right. So, and that's kind of it. That's the simplest format. Other formats are more complicated. And again, I'm not sure how like pseudocode versus not this specification should be. So I'm just gonna go with this for now. In some other functions, the kind of pseudocodeness will be more apparent, because some of this stuff is like Quaternion encoding in particular is slightly more intricate, and I don't think I want to spell out like the C code used exactly. Anyway, so that's kind of it, and now let's just convert the thing we already have. The SIMD implementation we already have to use SSE. So the way the SIMD implementation works is it takes the 4 values, 4 inputs, and then just does these computations exactly as they are specified here, except that this final, well, not the final computation, I guess, this part, this part of the computation, instead of doing this in floating point values, we just manufacture this value using the using the bit arithmetics, because we know that the exponent is in specific bits of the value, and so we just put the bits there, and this gives us 2 to the power of e. Much faster than we would be able to do this otherwise. And our C code uses the same trick. Basically, this is the computation. Like, we need to add 127 for unknown reasons. Right, to bias the exponent into the floating point range. And then we need to just shift by 23 to kind of move the bits in the right place, and that's it. And this is why it doesn't work for the full range of the exponent, but we don't really need the full range of the exponent. Oh, this encoding obviously can't represent things like infinities and nands. It also has 2 zeros, does it? Oh, it only has 1 zero actually, because the mantissa here is 2 complement. It only has 1 zero, but it has redundant encodings for a lot of values, just because it uses a mantissa where all of the bits of the mantissa are spelled out. Anyway, so this file right now doesn't have any SIMD implementations, so I'm just gonna steal some macros that oh boy, I don't want to steal all of the macros. So unlike the other stuff that I was doing in this library, this code I think will just be SSE2. So we'll just keep it simple. The only caveat is on Microsoft's implementation, I don't know if this is sufficient. there's like weird rules in C around, you know, which compiler defines which macros for SSE2 compatible stuff. For now, we'll ignore this and just assume goodwill. I think our header is XMM and written. Assuming. All right, and we'll just take our function, we'll just copy it, and then we will just replace the intrinsics with kind of their SSE equivalents. And I don't think for this first function we'll have to do anything else. I was thinking for a while now, after I started being involved with the WebAssembly and such, that maybe it's not a bad idea to kind of write a wrapping header. Like, there's all of these different wrapping headers between SSE and Neon, like one way, the other way, and people come up with some other custom stuff. But it would be kind of neat, so like WebAssembly, people spent a lot of time trying to find the right balance between performance and portability, and it's kind of not a terrible idea to just define these macros, define these as macros potentially, or as functions in terms of SSE code, and then just like you can write WebAssembly SIMD code and it just compiles onto anything. It's not the fastest way to do this though, so anyway, the SSE type, for people who don't know, for like vector registry is M128, or rather the type is M128I for integers and M128 for floats. This is mostly this code. All of these functions are going to be like half integer, half float. So we will do something like this. And SSE intrinsics are horrible, so you have to cast stuff in like weird random places for unknown reasons, but whatever. Usually when I write SSE code, there's this beautiful intrinsics guide that Intel has put up, which is basically, it's like a web page where you can search for things that you might need. So you can just say, okay, I need shift right. Well, okay, it doesn't work. I need shift right. And you can pretty quickly find, okay, I need shift right. What is this? Arithmetic 32-bit. No, not this one. Damn it. This one. Okay, cool. There's an instruction. There's an intrinsic. It maps to one instruction. And it takes like it takes one cycle of latency, and you can do like 2 of them per cycle on Skylake. And it even shows you in pseudocode, which is not very readable, but what can you do? What the instruction actually does. All right, so anyway. And if you work a lot on SSE code or Neon code or whatever, you tend to like remember these names of the intrinsics, but then they tend to evaporate, at least from my memory, over time. And so I'm gonna be looking things up. I'm assuming there's just an SLI. SLLI, okay, whatever. For left shifts, as usual, there's like 1 of them, but for right shifts there's 2 of them. Logical and arithmetic. And I'm not gonna comment on like the actual code, because this doesn't do anything special here. It just does this like 4 times up until now. And then we need to, so this code computes 2 to the power of x by, this code computes 2 to the power of x. As an integer. and there is some way to like convert it, but whatever. And then this just takes the mantissa, does the sign extension, which is this thing, and then just converts it to a floating point value, and there's the intrinsic for that. Convert PS, CTPS, something. Like as I was saying, you need to get into the correct mindset to predict the instruction names. Yeah, this guy. It converts the 32-bit integers to floating point. Intel SSE intrinsics are like the worst, absolutely the worst thing that I've ever used. Like, intrinsics have a bad rep. You know, you look at the intrinsics code and it's like, oh my god, this is crazy, this is scary, it's hard to read. And honestly, Intel's is just way worse than anything else. But what can you do? Like, why are 32-bit integers EPI 32 and floating point values PS? P stands for packed, S stands for scalar. Great, but like, it's completely inconsistent, right? The names are just all over the place. There is a pattern to them, which you can internalize once you work a lot with this stuff, but... Alright, so when we convert... So we compute the mantissa, we compute the exponent, and we multiply, or like the power of the exponent, we multiply them together. We need this bitcast thing. I don't know what it's called. Cast something. Yeah, this. So we need to take the 2 to the power of exponent that we computed as an integer, and then bitcast it to a float, multiply, and then store. Oh, actually, I think for stores, SSE is weird. I think for stores it's a float, if I remember right. Right. Let's see if this code compiles. And I'm just gonna use Clang for now. Oh, sorry, GCC. Just, I don't know. Like, I need to use one compiler to not constantly flip back and forth between them. Right, so... Oh, God. Oh, it would be also nice to know if the code that we are writing works. You know, just as a sanity check. To do that, we are going to run our unit tests, which we have. Okay. Just to check that our unit tests work and that our SSE function is actually like, you know, executed and such. Let's break something. For example, let's say that instead of shifting the exponent by like 127, we will shift it by 126, which should bias all of our results, which breaks our unit tests, which is great. All right, so we did not get faster. Like, we are still running at like 12 or whatever gigabytes a second with this last column, but hopefully... Where was my... Oh, I already closed the Microsoft Visual Studio thing. But like, okay, we can run this with Clang now and hopefully we'll get the same performance. Yeah, which we didn't before. Previous to Clang was running at like 4 gigabytes a second because it didn't vectorize this code. All right, so the simple part is out of the way, or the simpler part is out of the way. Let's go to the Quaternion function. The Quaternion function is probably the most intricate because it has this specific part about the encoding that is like slightly tricky to decode. Let me switch to chat. Yeah, one colo is saying it's CPI 32 due to legacy stuff because 32-bit is extended, which is the same naming as EAX, which I guess makes sense. Although for 64-bit, I believe it's EPI 64 and ARAX. And also it's EPI 16 in the intrinsics. Right? Or maybe in MMX it's not, but in SSE it definitely is. So I don't know. Like, I feel like all of these names are just historical accidents, like a chain of historical accidents that happened. It's like the suffix for the floating point ones is like PS and such, and then the suffix for these integer ones, I don't know. Like, it sort of makes sense, but also sort of doesn't. Okay, like, why is load PS? Why does that take a float? And like, the integer equivalent takes a register pointer. Like, all of the code that I've seen, like, whenever you use this function, you always have to cast the pointer because it's never of this type, just never is. So, I don't know. Anyway, whatever. All of this doesn't matter too much. It's just unfortunate that we ended up with these names that are like long and weird and stuff like this. Yeah, PS is precision single, no, so PD is precision double. And there is also SS and SD for single, for like scalar versions. Sorry, I think PS is packed single, not precision. No, it's packed single, packed double, scalar single, and scalar double. You can see the SS variants basically for all floating point stuff. Like this thing just adds a single scalar in the XMEM register, and this is useful because if you just want to add a single float, you otherwise would be forced to use x87, which is the preprocessor from like 40 years ago, whenever that was, 30 years ago, I don't know, which has its own problems. So yeah, I think it's either a single, but it's probably like scalar single packed single, scalar double packed double. Anyhow. Alright, so let's do the Quaternion encoding. The Quaternion encoding is a bit more fun. Let me try to remember how it works first. The interesting thing about all three, so there was a fourth encoding, the fourth filter that I wanted to add for colors, like I tweeted about this recently, but I didn't do this yet. And there's like one interesting reason as to why. So all of the filters that I have so far, they're all variable bitrate. It doesn't really mean variable bitrate, like maybe variable precision is a better way to put this. So in here, for example, right, as I was saying, for this exponential encoding, some values have redundant encodings. Like if you wanted to encode 2, you could encode this as 2 times 2 to the power of 0, or 1 times 2 to the power of 1, or perhaps 4 times 2 to the power of minus 1, etc. But also you could say, well, my mantissa is, instead of using the full 24 bits for mantissa, I'm actually going to use like 5 bits. And that's just what I'm going to store. And you would think this is wasteful because you're still using a 32-bit value, but the whole point of this filters is to make data more compressible by the compressor, by the codec. And if you have like a 5-bit value and you feed the resulting 30, like if you have a 32-bit value where there's 5 bits that are actually used and the rest is not used, you feed this to the codec and the codec compresses everything that's not used to like nothing or almost nothing, depending. And so all of the other encoding schemes follow the same pattern. All of the other filters here follow the same pattern, where there's actually a variable amount of bits that you could choose to use. And so when we encode the Quaternion, let's just spell it out loud. I have to like do this mental switches between talking and then writing code and writing like spec text that might be legible and like reasonably coherent for you know, other people to read. So bear with me for a bit. And so the Quaternion filter is a bit interesting because you encode the unit length Quaternion, but when the filter finishes, it doesn't produce 4 floats actually, it produces 4 floats encoded into 16-bit integers. So we could say that Quaternion filter how do I say this? Actually, I'm just gonna say the input to the filter is 3 Quaternion components, excluding the component with the largest magnitude, encoded as signed normalized 16-bit integers, and an index of the largest component that is emitted in the encoding. The largest component is assumed to always be positive, which is possible due to Quaternion double cover. I'm going to explain what this means in a second. Okay. So this is technically slightly incorrect. K-bit integers. K is not greater than 16. To allow per element control over K, the and this is gonna be the hardest one to like explain probably because it's slightly weird. The missing the fourth explicitly encode 1.0 as a k-bit integer in the same 16-bit integer slot that stores the index of the largest component. Alright, so this probably didn't really make any sense, but let's try to write pseudocode for this and then hopefully it will make more sense. So the input is 4 16-bit integers, and the output is 4 16-bit integers. The output is going to be the Quaternion, where the components are just normalized 16-bit. The input, however, is more complex. So the input says that the first three components are just encoded as normalized integers. So what we need to do is we just need to divide them by the magnitude. Like if the, for example, if k, so I'm gonna remove this because this is not really, like, k is not used in encoding. But let's say k is 16, which is like the basic case where the input is actually 16-bit integers. Then what we need to do is we need to decode the integers into floating point values. So let's say that this is x is input 0 divided by this. And then we'll do the same here. So now we have three components of the Quaternion. And then we need to reconstruct the fourth one. So this is just square root of 1 minus x times x minus 1 times y minus z times z. And you need to clamp the like the thing you're feeding into the square root to 0, because of the imprecision in the input, you may actually get the result that's like more than 1 perhaps, and then square root will return a none, and that's just a bad time for everyone. So this is like the basic Quaternion encoding that you could imagine, where the input is a normalized Quaternion. These guys are signed integers, right? So these guys are like signed floating point values. I should probably do this to be consistent. And this value is always positive. The reason why this is possible to do is because for every Quaternion, there's two Quaternions that represent the same rotation. This one and this one. So you can negate all of the components if you want, and because of this you can always assume that the component of your choosing can always be non-negative. However, this is a bad way to decode a Quaternion. The reason is the square root loses precision, or the reconstruction, like done this way, loses precision as the value that you're reconstructing gets smaller. And so if these guys are actually large and this value is small, the resulting Quaternion will have a lot of drift compared to the value that you started from. Because of this, what you should do is you should reconstruct the largest component, because that minimizes the resulting angular error. However, what if the largest component was not the last one? Well, the answer is, let's just reconstruct the largest component and then kind of rotate the values so that whichever one we're reconstructing is going to become the largest, if that makes sense. Like if the largest was number 2 instead of number 3, then we'll just encode the other components and we'll encode the number 2, like the index of the largest component, and then when we are reconstructing, we'll reconstruct in the right way. So to do that, we and there was one more thing I forgot to mention. So let's just do these step by step. So there is this component index max component max comp, which is stored in the so there's just 4 components, so we just need 2 bits, so it's just stored in the last 2 bits of the third input. Now that we have this component value, we can say, well, now let's just reconstruct, like let's just basically put the decoded components of the quaternion in the right place. And the way to do this is, and I forget what exactly I use, like basically I use a rotation scheme where if you say max component is 0, you store components 1 to 3. If you say max component 1, you store components 3 to 0, and then 2 like 3 0 1 3 0 1 2. So this is kind of the order, except that maybe it's a slightly different order because it doesn't fundamentally matter. But this order is like, you could say, oh yeah, if it's 1, actually we'll store 0 to 3. And it is convenient to be able to just rotate through the components so that, you know, if you imagine like an infinite sequence of 0, 1, 2, 3, then it's still the same order that you're storing things in. You're just omitting one of them. You're like starting the sequence from the value that's not the first one. So and for reasons unknown, I don't actually use this fact in my scalar decoding function. Let's actually fix this. It would be nice if the pseudocode that I'm writing in the spec is basically very similar to the scalar code that actually works. But yeah, so like once we know kind of the order of the components, right, we can just say, well, let's just store the output. Let's just store these values to the output, right? Except that our output is 16-bit integer, so actually we are gonna store this, right? And the reason why the output is 16-bit integer is because the filters work in place. Like they take the value decoded and put it back in. And GLTF supports 16-bit integer quaternions, so this is like a nice way to. It's just like it's kind of hard to explain like the entire chain of reasoning that led to this, but there is a few things like you say, oh, okay, I want to minimize the size of the memory. GLTF supports 16-bit quaternions. Cool. I need to encode 16-bit quaternions. Okay, I need to minimize the size in transmission. So I need to encode 16 bits. I need to encode something into 16-bit quaternions when I'm loading the file. The encoding has to be really fast, so it would be good if it worked in place. The encoding has to be friendly to my byte encoder, etc., etc. There's like this chain of reasoning that basically eliminates most extra possibilities along the way. Anyway, so this is what we need to do, and the question is kind of what do we store for these, like where do we store these inputs, right? Not inputs, sorry. Where do we store the computed results? So, if max component is 3, so we are reconstructing the max component. So if max component is 3, then this really should say 3, right? And then this is kind of what it is, right? And so what this boils down to is that this guy should say max comp, and this should say max comp plus 1 modulo 4, and this should say max comp plus 2 modulo 4, and this should say max comp plus 3 modulo 4. And this just is, you know, this. And this is a rotation, right? So I'm gonna say max comp specifies a cyclic rotation. I guess all rotations are cyclic of the values. And so again, for reasons unknown, I don't actually do this in my scalar code. Let's actually do this in my, oh, no, okay, it's all good, I think, yes. Let's see, maybe it makes the scalar code a bit faster, or maybe like GCC starts vectorizing the scalar code. So we're looking at the Quaternion stuff, which decodes at 800 megabytes a second without I will cover this in a second. So yeah, really basically what this should be. Yeah, really the thing I wrote in the specs should just work. So let's test this. And instead of plus, we will use an and. How does and? Oh god. All right. Alright, so this is the cyclic encoding. It probably still works. Oh, right. I don't need this table anymore. My unit tests still pass. Alright, this is a touch faster on the scalar code, which is nice. Let's check that the unit test actually, yeah, okay. Alright, so, and we'll go over how to do this in SIMD code in a second. Now, the one thing that we are not doing yet, like our spec isn't fully correct. The reason why our spec isn't fully correct is, there's two reasons why our spec isn't fully correct. So one reason is there's this K thing that I started talking about, right? Where this is good if you want to store inputs as 16-bit, but sometimes you don't want inputs as 16-bit. For example, I found that for most animation data, using something like 12-bit inputs with this encoding is actually plenty. It generates like really good resulting errors. I think this is the default that I'm using for my like GLTF pack program that actually compresses all of this stuff. But you could choose to say 15 or 8 or something. 8 is like not enough. Or I think the useful range basically goes from like 8 or 9 to like, 13, 14. But there is a kind of cool thing that I don't think I do yet. Yeah, I don't do this yet, but I experimented with a neat thing where you vary the, so imagine you have like an animation sequence, right? And so if you have roots of the tree in the skeleton, you need more precision to compress them, because as you animate these roots, the error propagates down the chain of the skeleton. And I experimented with a thing where the number of bits used for this encoding was adaptive based on not quite the depth of the tree, it's kind of more interesting, based on the furthest, let's say, bone, based on the distance between like the bone's origin and any other bone that's furthest from that in the world space in the skeleton. And this is kind of the bone influence radius. Like you could think about this like this. If I change the angle of rotation by 1 degree, what's the worst case linear motion that can result from that? And the answer is, well, you need like to find the vertex, but for simplicity, let's say you need to find the bone that's furthest away in terms of distance, cumulative distance from that bone, and then you need to take that linear distance and then just ask like what's the motion of the point that's that far away from the origin under a 1 degree rotation. Anyway, and this works really well. This allows you to kind of balance the error that you're getting so that you use more bits for the roots of the tree and fewer bits for the leaves of the tree. So because of this, we are saying that in addition to encoding these 3 components, and in addition to encoding the 2-bit index in the last component serves a double duty. It also encodes the value of 1. Well, let's just say 1. And this is going to be input. The last 2 components store the index of the maximum one, so we need to like clear them out. But then if you do this, you're effectively getting again a 1-bit integer, a k-bit integer, and basically you can do that. So we are saying like the third component, did I write this down? Hold on. Wait. The last input element explicitly encodes 1.0 as a k-bit integer in the same, well, except for the least significant 2 bits that store the index of the maximum component. And so here basically the convention is the last input stores 1.0 encoded with the same number of bits as these other guys. And because of this, you can just divide this by that and you will get the correct value. And the final tweak to this encoding, so this is almost correct now. The final tweak to this encoding is that since we are reconstructing the maximum value, the maximum component, and the input quaternion is normalized, the maximum value of all of the other components is actually not 1. Like the values aren't -1 to 1. The values are minus square root of 2 over 2, I believe. Like the value range after you eliminate the maximum component is this. Is this right? The worst case is there are 2 of them. Yes, this is right, which is equivalent to -1 over square root of 2. Yes. So after this decoding, we get a value that's in the range of -1, right? So to accommodate this extra factor, we will modify this by the scale or by the range, right? Where the range is just a constant square root of 2. All right. And so I think this is the complete encoding. After eliminating the maximum component, the maximum value of the remaining components is 1 over square root of 2. The maximum magnitude, I guess. Because of this, the input, the remaining components are stored. How do I put this? The input components are stored. How do I write this like in English? Store the original component value scaled by square root of 2 to increase precision or whatever. This is neat. This buys you like half a bit or something per component. All right, so I think this is the complete description of the thing that's going on here. of the Quaternion components. All right. This should probably say something like input 3 encodes a k-bit representation of 1.0 except for bottom 2 bits. All right. I was happy when I came up with this. I was initially like hard coding the K to like 12 or whatever, and then I figured, well, it's actually a bad idea to do this, and then I came up with this, and this kind of all works well. And like again, it may seem like we are kind of being inefficient here, so we are using extra 16 bits to store what's effectively a 2-bit value plus like a constant, but because all of this gets fed into another compressor, it kind of takes all of this inefficiency away, and so what remains is a very compact, like in this output, in this third input component, we are effectively storing just the 2 bits after the compression takes effect, which is nice. All right. So this was it. We already have a SIMD version of this for WebAssembly. We need to convert it. All of this stuff is like really straightforward. You can look at this, it just does these basic transformations. The only thing that's not really straightforward is this. Or actually, there's some issues here as well. But let me look at the chat. There was a question. Didn't the first Pentium have a weird bug with the vision? Yeah, I'm not sure. I'm not sure what the context is, but yeah, there was a bug in fdiff, which is from, oh, maybe I was talking about x87. Yeah, there was a bug in fdiff instruction, x87 coprocessor in like Pentium 4, was it? Earlier? I don't know. Maybe, probably earlier. It can't be Pentium 4. No, yeah. Like when the coprocessor was introduced, so Pentium like before 1, or Pentium 1 or something. That was fun. Intel processors have lots of hardware bugs these days in complex instruction architectures. Like there is a, what's it called, SGX, I think. SGX instruction set extension that, not SGX, TSX, that provides support for transactional memory, and I think it had bugs in like many revisions of the processors. Sometimes these bugs, and there are bugs in some other more basic things. Some of these bugs are patched. There is this really horrible bug. Oh, no, that's a performance bug. Whatever. Like some of these bugs are patched in microcode. Some of these bugs are just patched by like disabling the instruction set extension and then waiting for the next year to ship. So, have I tried different ways of encoding Quaternions other than smallest 3? Yes, I have. So smallest 3 tends to be, in my experience, like what I found, it's the best practical way to do this. There is a few more esoteric maps. Let me see if I can find them. Yeah. So if you're, is this? Yeah. So I think this is the blog article that summarizes a bunch of the other options. I feel like, oh yes, actually, this is the one that I was thinking. It's the same author. Yeah. So there's this article that summarizes a lot of the other ways to do this. The largest, like the thing I'm using is somewhere here. Don't remember. Is it the Cayley transform? No, the smallest 3. So yeah, so like this is what we are doing. Where is it on these comparisons. These are Euler angles, I want to say. Oh, ST, right. ST is the smallest tree. So you can see it's really hard, like all of these colors blend together for me. Not all of them, but like most of them. But anyway, so there's this blog post that talks about details. I tried this stuff. There's other encodings that are more effective in terms of giving you more precision for the amount of bits that you spend. However, they are slower to decode, and it's not clear that the result is worth it. Oh yeah, actually, so here you can see that there's a delta. So I think this is the error for like X bits. So let's say we are using 15 bits, and there's an error. Who knows what the value of the error is? What is the value of the error? I don't know what the units are here, but here for this bit range is like 15 for small 3 and like 9.74 or whatever for X map. So it sounds like smallest 3 is within like 1.5x or whatever of optimal, if you know these are optimal. It's much faster to decode. And also I think the average error tends to be better for smallest 3 comparatively. Not better than these other ones, but it's not as much worse. But anyway, so like smallest 3 I find is the best practical one. I've learned about smallest 3, I want to say in like 2008 or so. So like 12 years ago. And honestly, I haven't really seen a practical encoding that's better by kind of enough that I would want to use it, if that makes sense. But certainly I could be wrong. Like maybe, so yeah, like I looked into some of this stuff. It's not. So like the inverse transform for this exponential map has a sign in it, right? And like you don't want the sine and a cosine, and you don't want this anywhere near your like fast quaternion decoding functions, right? So this one is much better. Basic harmonic mean. So I guess it's H min, but it's not as good in terms of error. It's pretty close. So maybe like H mean is actually better, right? I don't know. Have to do some other stuff though. Oh wait, was I looking at the right? Yeah. Oh okay. No, well you have to. Yeah. Like it's not as bad, but it's like way more work still. Which, you know, like it could be the right trade-off. I'm not sure. I think I implemented all of these in context of my animation compression stuff, and I think when I looked at the errors, like these gains were not as convincing, and then I just said I think it's better to use the smallest 3. So there are different ways to compress quaternions. None of them are like better in a groundbreaking way. Like, you know, since the delta is like 1.5x, this basically amounts to like storing 1 extra bit or something, which 1 bit is sort of a lot in compression parlance, but also it may not be worth fighting for quite as much. Compared to this, I can tell you that the smallest 3 is dramatically better than not doing smallest 3 and just storing the components as is, like raw. In fact, smallest 3 gives you much better precision than storing the components raw for like complicated reasons. Anyway, all right. I've talked enough about this stuff. Let's just do the SIMD thing. So the SIMD thing, there's this really long function that we are gonna convert to SSE code. I'm getting a bit hoarse. Need more tea. So I'm gonna start with the one-to-one mapping of this to SSE2. I don't remember what this maps to. Most of this stuff is straightforward, like we just did the same thing. Some other stuff isn't as straightforward. But yeah, I'll start with just a one-to-one mapping, and then when I was thinking about this, there's a couple of places where for WebAssembly SIMD I was doing like sketchy things. It would be neat to just get the code to like work, and then we can fix the sketchy things one by one. And this stuff was a bit sketchy as well. So we can fix this one by one and see if we get a better... Why did this not... Did they just not want to deal with this? Anyway, like basically we'll see what the one-to-one conversion from WebAssembly SIMD to SSE2 looks like, and then try to maybe improve performance or reduce the like amount of weird stuff we do in this code because of WebAssembly shenanigans, in hopes that this will get us faster, get us to run faster. Types are gonna be fun. So the nice thing about WebAssembly is that there's just a single type, which you would think is actually a bad idea. Because, you know, like type safety is good and such. But actually I found in general, as a like rule of thumb, when working on CMD code, non-type safe intrinsic sets tend to be more pleasant to work with. I hate this thing. These load intrinsics are just... like... It's not too bad, it's just it's like frustrating to work with this stuff. Anyway. So shift right arithmetic immediate. Oops. And then this guy is shift left logical immediate. The reason why this conversion is so straightforward is because when I was writing WebAssembly code, I had a mental model of SSE2 in mind, and so I was doing things that were efficient there. And there's like this whole art to writing fast WebAssembly SIMD code that maybe I'll make a separate stream about at some point. But yeah, so far, as I was saying like earlier, a lot of this is just really straightforward conversion from scalar code to vector code. Like this is ending 4 integers with a vector of 4 integers that have 3 in them, which is like this thing just done 4 times in SSE, right? So there's nothing particularly interesting here. Technically, I should probably extract this out. I don't remember why I didn't do this. It's fine. I'm using divisions here. Technically, you can multiply by an inverse, but you have to compute this is kind of where, so I wrote this line in the very beginning where I said, hey, maybe it makes sense to specify the behavior up to 1 unit in the last place of the resulting value. And this is because you might want to do certain things for performance that drop your quality a tiny bit. But as I said, maybe it turns out it was a bad idea all along, and we will not do this. Alright, so I have a blog post about this general approach to writing SIMD code where you just do a scalar thing like 4 times, which, if anybody is curious, no, not here. I think it's the optimizing slur particle. This is just a great simple way to write most SIMD code. Like, I feel like basically probably 75% of useful SIMD code or more is just, you know, you want to do X 4 times, just mechanical transformation of the code, done, which is great. It doesn't always work, but when it does, it's good. Oh, there's this extract lanes which aren't even SSE2. Oof. Yeah. So this code, I think I will have to rewrite pretty substantially in a bit for a couple of reasons. But let me first finish converting stuff. So there's these 2 operations. I don't actually remember what they do, but oh, they map to shuffles. I think this does something like yeah, it says let me get the first 2 components, 32-bit components of the first, or no, right, not the first. It basically says let me take components 0 and 2 from the first vector, and then 0 and 2 from the second vector, and then the next line says let me take components 0 and 1 and 3 and 1 and 3. To do this in SSE, there is an instruction called meshop something. This guy, which frustratingly exists only in floating point equivalent, which is fine for our use case because we are doing this on like 32-bit values, so it's the same computation. But it's painful because we have to like let's load these guys. Do I use them later? No. Let's load them as floats, I guess. And then we will shuffle these guys. Now, so now there's this bits where I really hate the intrinsic set. It's not the instruction set really, it's the intrinsic set. So there's this immediate, and there's this macro, and then shuffle PS, is it? But this macro has the arguments in the wrong order. Is it just a shuffle? It had like, yeah. So it had the arguments in the wrong order. So you have to say like 2020. And I will never know why the arguments are in the wrong order, because I think I think in byte like values they are in the right order, depending on what you think the order of bits in the byte is. Anyway, whatever. So these are not my favorite parts of the SIMD stuff. When working on SIMD for like if you have a large production application where you need to write a lot of SIMD code, you should probably not write intrinsics directly. There's a couple of ways to not do this most effectively. However, you can find the wrapper library, you can write a wrapper library, you can use ISPC, things like that. In my case, it's slightly unique because I'm working on a library, and it's really important for me that the library doesn't come with dependencies. So you just drop it in, you compile it, and so I can't really afford these like nice things, unfortunately. And because of this, I need to suffer a bit, but that's fine. So this is the part where I'm just gonna do the right thing. Like, I'm using an integer max here because WebAssembly max is slow. But really there's no need to do this in SSE code. Alright. And I'm pretty sure this code is stupid, like you don't need to do this, but for now I'm gonna do the exact same thing to not think about this. So I think these map directly to unpack. I'm sorry if I'm going fast and this is like not comprehensible, but I wanna finish this stuff like today and there's one more function, or actually two more functions to go through. Maybe I won't finish this today, but I just don't want to spend too much time like explaining things within reason, of course. I feel like I sort of explained things enough. Yeah, so up till this point, all of this was kind of business as usual, just like do things 4 times. This is the part, oh, I didn't even explain the structure of the loop. No, well, like whatever, there's like 4 quaternions that we are filtering, right? So you just do everything 4 times. There's 4 inputs, 4 outputs. But so we need to do this computation where we do a cycle like 4 times for 4 component values, right? And so in my WebAssembly code, the best thing that I found to work with the current limitations was to take so each quaternion, when we encode it, is 4 16-bit integers, which means 8 bytes, which means it's a 64-bit integer, right? And so you can take the 64-bit integer and just literally rotate the bits using the rotate instructions. Because this transform is a rotation, and this is why it's a rotation, to make sure that it's possible to implement it as a rotation. And so this is what this code does. It just reads the 64-bit values and then just like shifts them, like rotates them using the rotate intrinsics. Now the problem is, like the first problem is it's not super fast necessarily. Like it's also not super slow, but like it's not clear if this is the optimal way to do this. And the second problem is that to do this we need to extract the 64-bit components out of the SIMD vector. And there's like not a good way to do this up until who knows when. So SSE 4.1 is the one where you can do this easily. Temporarily, we're gonna succumb to the pressure, enable SSE 4.1, which I don't want to do because not all processors have this, etc. Temporarily, I'm gonna do this. And then we will fix that later, but this allows me to like get this code to run. So the most frustrating part of working on SIMD code is when you spend like, you know, hours writing this code and then you run it and then it doesn't work. And almost always the bug is really trivial. It's like there's one place somewhere in the code where there's like, not one necessarily, maybe there's like 7 lines with bugs, but all 7 bugs are like really trivial. It's like, oh, there's a typo here, or the argument order is wrong or something. But every time it takes forever to find the problem, because that's just how things are. And somehow, like, SIMD code is really, I found, it's sort of typical in programming, but like somehow in SIMD code I found that this happens a whole lot more than it does in some other areas. All right. I guess it doesn't differentiate between... It's kind of weird. Alright, whatever. Let's just get the code to compile first. So it doesn't like... Right, so I guess this is the point where I need to cast... Ugh. Oh, wait. What? Hold on. Oh, right. So I'm doing this really weird sketchy thing here where, and I'm pretty sure it's a bad idea, where it's a great idea in WebAssembly, but I'm pretty sure it's a bad idea in like actual SSE code, where I'm converting floating point values to integers. Maybe it's not a bad idea in... It's kind of interesting. So like I'm converting floating point values to integers using this trick from who knows when, where if you add a large enough floating point value to a floating point value, the resulting floating point value can be thought of as an integer, like you can just read the integer bits out of the result. This works great for WebAssembly. But I think it works great for mostly the wrong reasons, because the WebAssembly SIMD doesn't have a fast instruction to convert, like to do the same thing basically. So we'll see if we actually need to do this stuff. Why do I need... I'm a bit confused though. Oh, built-in rotate left doesn't... No, like it doesn't... Okay, whatever. Uh-huh. Yeah. Clang has this, right? Yeah. So Clang has rotate intrinsic. GCC, I guess, doesn't. Is that right? Oh, but it probably has like roll or something like this. No. Microsoft's compiler has an intrinsic for this. Maybe GCC just relies on like pattern matching. Alright, I am going to just use Clang for now. Like, I think I should replace this stuff anyhow, because this is the only thing that requires SSE4.1, which is probably not good. And this needs this rotate left, which in WebAssembly it's actually easy because it's just a single compilation target. But here it's actually like it's always Clang and stuff like this. But here Clang has an intrinsic, Microsoft's Visual Studio has an intrinsic with a different name. GCC doesn't have an intrinsic, so you have to... It's... I don't want to talk about this. Rotates are terrible in C. For really no good reason at all. Alright. Oh. Miraculously, our code worked, which I super didn't expect. Or maybe our tests are busted, but like we know the trick, right? Let's change some value. Aha, tests work. So the code works, which is simultaneously not surprising and shocking. Is the code fast? So the code runs roughly at the same, so WebAssembly ran at 2.6 and we are running at 2.9 roughly. But we are not done yet. Let's now see if we can make this faster. But before we do so, I want to get, I'm getting cold, I want to get more tea. And I will see if chat has any questions or whatever. Okay, I am back. Chat does not have more questions. So our code runs. Our code requires SSE4.1, which is not cool. It doesn't compile on like any compiler that's not Clang, which is not cool. And it's slightly faster on WebAssembly. You know, WebAssembly runs at like 2.6 and we run at like 2.9. But I have a feeling that we should be able to do better just because WebAssembly SIMD is a bit constraining in terms of like you can't really hand code for the hardware, and here we can hand code for the hardware. So we should really be able to do better. So let's see how we will do that. There's really two parts. I think everything here is doing a reasonably basic thing, reasonably optimally. Like maybe there is one or two things that we can optimize somewhere here. Like maybe instead of the division, we should do the reciprocal multiply thing, but that loses precision, so maybe that's a bad idea. My unit tests right now, I think, are tuned to just like, is this stream working? Whatever. Or if this is really a problem on the YouTube side. Okay. Comcast again. What if I do the gameable speed test, the one that lies to you? I hate debugging stream problems on stream. Okay. So this is like way more bandwidth than what YouTube is getting. So clearly my connection to YouTube, I mean, maybe Comcast is just lying, or maybe there's like connectivity problems elsewhere in the internet. But clearly Comcast thinks it's okay. I mean, like 3 megabits upload is not, is like nothing to write home about, but it's better than this. What is this? Half a megabit? Alright, I don't know if the stream even is working at this point. And I'm worried that it just doesn't. Let me try to see. It's doing a reasonably basic. What if I do the... It's doing a reasonably basic thing, reasonably optimally. Like maybe there is one or two things that we can optimize somewhere here. Like maybe instead of the gameable speed test. The content is there. I just don't know, like it keeps cutting out. YouTube is horrible. Can somebody who's watching this write in chat about kind of what their experience of watching the stream is in the last like 5 minutes? Do you see video? Do you hear audio? Or do you just like hear nothing? I guess if you hear nothing, you will not be able to write in chat. Because if it sort of works, then like whatever. We can keep going. It worries me that the viewer count is constantly bouncing. It's really frustrating with the amount of money that I pay Comcast every month. Which you guys don't want to know how much that is, but it's a lot. It's frustrating that the quality... Yeah, starting and stopping, great. Oh. This could be bandwidth problems on... Well, this is not. Okay. Okay, I'm gonna have to restart this. Okay. So that is back. This thing says it's an excellent connection, but I'm inclined to just believe it. Let's just see. Okay, maybe we are back. Because I don't know. Let's just assume we are back. And let's just keep going. like the stream status says excellent, which I'm sure it will change in like a few minutes when we start actually doing stuff, but maybe it was a router problem. All of this is so frustrating. Like, yeah. I really need to, I think you can like buy probably better routers than what Comcast gives you, but it's always such a hassle to kind of like do anything with network equipment that I never do this. And then it turns out I should have done this, and that would, you know, save me a lot of headache. But anyway, so I guess things work now. And stream status says excellent, so I'm just gonna assume it works, and we'll just keep going. All right. So before the internet, or I guess the internet was fine, like maybe it's a router problem. Let's assume it was a router problem. So before my router decided that terrible upload speeds are fine, we were dealing with possible optimizations. So one possible optimization is that right now we are doing this floating point to integer cast in a really weird way where we add a very large floating point number. And it actually probably is still the fastest way to do this, but I just am wondering, so there is like an intrinsic to do this, which doesn't necessarily round to nearest integer, but I want to say that by default it does do that. And so let's just try to use this and see what happens. And if it's not faster, then maybe I don't want to do this. Or maybe I do. I haven't decided yet. Let's see if this even works first. And if it's any faster. So it's not faster, but also it's not slower. So the problem with this instruction is that it assumes that the rounding mode is set to nearest, but also my previous thing that I was doing assumes the same thing. And if you aren't setting rounding mode to nearest, I don't know what you're setting it to. So maybe it's fine. So let's just do this because it's cleaner and simpler, and you know, it's not slower. It's not faster, but it's not slower. Alright, so the only real thing it looks like that is actually interesting for us to change is this whole thing. Does the stream still work? I'm just paranoid now. Okay, the stream quality is poor now. Whatever, I'm gonna assume poor is actually good and no data is actually bad. Maybe that's a wrong assumption, but I don't have mental energy to deal with this. I don't think we are going to be finishing the whole thing. I think we're just going to finish the Quaternion stuff. And I can do the rest later-ish. So the dilemma goes as follows. We have four... cool. We have we have two vectors with two quaternions in each. So we have quaternion 0, quaternion 1 in result 0. And in result 1 we have quaternion 2 and quaternion 3. And these are using 64-bit integers for each. What we would like to do is we would like to take each one of those and shift it by some amount of bytes. Or not shift, like rotate it by some amount of bytes. So what are the ways to do this? So one thing that I was thinking at some point that we could do, and let's just see kind of how fast or slow, whatever it is. One thing I was thinking of is to do, what does this shift by, hold on. Right. So one way to kind of reorganize, like reorder components in a SIMD vector is with shuffles. Shuffles are an SSE2 feature, so I didn't really want to use them here, but I'm kind of curious as to whether it's actually even faster, I should say. So there's this instruction, I guess 2 of them. I guess I really need this one. Interesting. Okay. Like the problem is I have 2 quaternions in each vector and I have to shift them. I have to rotate them using like individual rotate masks, which is not great. But I don't really have good options to deal with that problem otherwise. So I'm just gonna try to do that. So we have 4 possibilities for the input. For the maximum component, right? And so for each one we could build a shuffle mask. I don't know, I've never worked with the M64 values. Like, I don't really know how do you set, like this. Can I do set PI 16? I can, okay. So the way the shuffles work is you have to specify the bytes that you want to get out of the value, out of like the input vector. And so for a shuffle mask, for a shuffle like vector to not change the input value, it basically has to be just 0, 1, 2, 3, 4, etc. I'm trying to figure out if these values are being flipped at all, like reversed. They probably are. Is there set R? Okay, cool. So this is a vector where if you use the special intrinsic on this vector, it will not change the value at all, which sounds pointless, but what happens if you do this, like this is a rotation of this vector to the left, to the right by 2 bytes, and so this I think should do a similar rotation to the actual 16-bit components of the vector, and so I feel like if we just have these stable, then I think it's kind of weird though, because I would need to use a shuffle on a 64-bit component, which is effectively equivalent to a rotate. And so I'm just using a shuffle instead of the rotate. But on the 64-bit architecture, like, rotates are just as fast, so what's the point? Yeah, this plan doesn't sound very good anymore. Well, like, it sounds fine, it's just a bit pointless. Maybe the thing I'm doing right now is just the fastest way to do this. I don't know. If it is the fastest way to do this, I would like it to not require SSE41 for no apparent reason, but that's a fixable problem. Let me think. Is there really nothing else I could do here? Because yeah, okay, so shuffles are a bad idea, because an 8-byte shuffle, I would just need to do them 4 times, and then it's the same as the code that I already have with rotates. I could do a shuffle once per the 16-byte vector, but then I need an array of 16 shuffle masks. Which is maybe fine, but it's not actually a very... Damn it, I don't know. Okay, let me try this. I don't know. I am starting to suspect that what I'm doing right now is actually the optimum, but maybe that's not true. So let's try to use shuffles. The way we are going to use shuffles is this. First, we are going to use the shuffles in a stupid way. Or actually, let's just use them in this... Ugh. It's going to be painful to even... There's 16 of these masks. Oh god. This is 256 bytes worth of data. It's a terrible idea. And I'm just gonna save... No, you know what? This is a terrible idea. I don't want to do this anymore. I want to explore other options. What other options do I even have? Like, so if I can't extract... Or I can extract and rotate. There's no... Well... So that's an option. While shifting in zeros and store the results in DST. Right, okay. So maybe this is the better option. I didn't take this option in Wasm because it didn't have vector shifts. But Intel, thank God, has vector shifts. Intel has vector shifts. Okay. Maybe this is... Yes, shuffle idea is terrible. I don't like this anymore. Okay, so let's try to do this. So what we are trying to do is this. We are trying to rotate a value, a 64-bit value left. And we are trying to rotate the 64-bit value left by the number that is specified or that can be computed, like from the data that we have. To shift something left, is this thing... Oh, do we have to mask this? Which is fine. So to shift the value, or so, to rotate the value left by, let's say, 5. You have to shift it left by 5, and then you have to shift it right by 5, and then you have to OR the results. Sorry. You have to shift it left by 5, and you have to shift it right by, like, the 64 minus 5, where 64 is the size of the value in bits. So if you're rotating a 64-bit value, like, this is what you need to do. So really we could just do that, where if we had a value that we need to shift by in a vector, and then we could just do this computation like exactly as written, so we can shift left, we can shift right, stuff like that. Now the challenge is So the challenge is the value that we have. There's two problems. So the first problem is this just trips me up. So the SSE shift instruction says that if you shift by more than 63, then you get 0. Which sounds like a good idea, except that the Intel's scalar instructions don't do that. The Intel scalar instructions say, hey, we're just gonna take the low, like whatever 6 bits of your value and like shift by that. And I'm just baffled by this. Okay, all right. So we need to make a shift mask, and to make a shift mask, we need to take the component index, we need to shift it by 4 for some reason. Right, because this is this multiplies by 16. And so because of this, we need to like end it. Oh god. Why is Intel so inconsistent? But okay, so this is the shift, this is the rotate amount, excuse me. To rotate by this value, we need to do this computation. However, we are doing this computation on 64-bit values. And this one is a 32-bit value, and there's like 4 32-bit values in the registers. So because of this, we need to spread it out to 2 64-bit values. I suspect the best way to do this is this guy, which I can never remember the order of these things. Let's see, so it takes the first this unpacks the low half. Hold on, I need to focus here. Yeah, I think this is right. Yeah. So this beautiful code takes the basically move 32-bit shift values into 64-bit or convert into 64-bit to 64-bit. Now we can use this guy to rotate. However, there's no rotate instruction, there's just a shift instruction. Because of this, we're gonna rotate the quaternions by the CM values manually. I guess I can just do this. So it's an OR where is that how it's like? Yeah, where we shift the value left and we shift the value right, but instead of shifting it by the same number, we are shifting this by 64 minus the same number. And so to get that, we need this guy. Thank God this is SSE2. Alright, and so this is the rotate. And then we just do this for the second quaternion component, and then we can finally store this thing. Store U. The reason why we need to do this twice is because each vector is 16 bytes, but there's 2 quaternions in it because each quaternion is 8 bytes, so we need to do the rotate twice. All right. Oh God, what? What? The hell? What? Who comes up with this stuff? So, alright, I just have no words for this. Alright, this did not work. Our unit tests have failed. Our unit tests have failed us. So this is the uncomfortable moment where we need to either figure out what's wrong with the code or debug the code. And I kind of didn't want to do either of those things. But I guess I have to. Like, I'm sure it's here somewhere. Do I have to... So if this shift value is 0, we're going to be shifting this by 0 and this by 64, which doesn't matter. Okay, I'm not sure what the bug is, but we'll need to debug this. At least the stream seems like it sort of works. So... Oh, this is wrong. This should be that. Wait. No, yes, this is right. Or I guess if I'm gonna be consistent. Doesn't help though. Am I sure it's not like this? It's not like this. And this code still works. Alright, you know what, let's just debug this. Let's just debug this. So I'm gonna put a breakpoint. Or actually, Let's see. What? Oh, I guess it shows 264-bit values. Interesting. Okay. So, let me look at my unit tests, because it's gonna be faster probably. C, D, E, F. Yeah, so my masks are 0, 1, 2, 3. Very easy to follow. So my shift values... Oh! Of course. Or not. Wait, hold on. Something is kind of odd here. Why is the rotate not... How does this whole thing work? Hold on. I think I'm not rotating by the right value or something like this, because... Like, let's say the component index is 0. Sorry, no. Let's say the component index is 3. This means that the maximum component is a W component. This means we shouldn't shift at all. How did the old code work? Because wouldn't it say component index 3, 3 times 16? Oh, because we pack in the wrong... Oh my god. Okay, alright. Okay, never mind. This is all good. So then we should just rotate. Okay, so then our rotate must not work. So this is 0, 16, 32, 48. Okay. Let me... It feels like something stupid. And I'm not doing the thing correctly. So you shift it right, shift it left by like 16 or whatever. And then you shift it right by 48. And then you OR the results. And then you get what you wanted. Why does this not work? This is confusing. Alright. 32-bit like rotate values to 64-bit shift values. Let's just say this. So like shift left, shift right. And there's this thing. And then shift right. And these are gonna be rotated results. Okay, shift left, shift right, 64 and 48. I think I got too excited about the, oh god. Don't tell me. Okay, that explains why it doesn't work. So this shift thing pretends like it's doing a vector shift, but it's actually doing a scalar shift. Yeah, I was like, it's caught me by surprise. I thought SSE doesn't have a vector shift, but then this thing clearly looked like a vector shift, and I was like, awesome, let me just do a vector shift. But so this is not a vector shift. It's taken the 64-bit value for whatever reason from a vector intrinsic register and like shifts every element by this value. So this is a scalar shift. This is not a vector shift. So this is not useful. This is like useless for my purpose. Okay. So the code didn't work because the code shouldn't have worked in the first place. Okay. At this point, I suspect that there's just no better way to do this. At this point, I suspect that whatever the code we used to use with scalar 64-bit shifts is just like the best way to do this. And the challenge being that we need to there's many things we need to solve here. Damn it. I mean, odds are it wouldn't have been faster anyway. Alright, that sucks, but what can you do? What else do we have? So we have these guys, but these don't work for this use case. Yes, I basically suspect at this point that the rotate implementation is the best we can do. We can try to do shuffles, but they're not like better. Okay. Okay. Alright. I just, at this point, I suspect there is not a better way to do this. At this point, I think that's the best we have. Okay. Assuming that's the best we have, let's drop the stupid like SSE41 or whatever it was requirement, because it's not actually like meaningful here. But yeah, maybe there's just no other way to do the CMD with the SSE instructions set. Maybe that's just the best we have. So the way we are going to do this is we need a function to actually do this rotate. Let's figure this stuff out later. So the classical way to do rotates, unfortunately, is to use basically this. But the problem with this code is that if x is 0, then this thing right shifts by 64. And right shifts by 64 are undefined. So the correct way to implement this is to do this. And I think this is lowered to the like optimum code, but I'm not sure. And like this behavior might be different between different compilers and stuff like this. But anyway, so because we are using rotates, it's not clear to me that we actually care about doing some of the stuff that we did. Oh, I should do this perhaps. Yeah. So I think this is the full kind of rotate implementation. So we probably don't really care about computing this stuff as like a vector. So we probably can just do something like I plus 0 times 4 plus 3 shifted by 4. So this is probably good enough. It's kind of unfortunate. I was hoping that there is a better way to do this, but maybe there just isn't. Okay. Oh, this is actually a tiny bit. Nah, it looks like it's about the same. Now, instead of this extract thing, we can should we just store, or is it a bad idea? Let's see. Oh. Well, yeah, okay. I'm not doing the right thing, hold on. So basically we just need to store these guys to the stack and then we just like load them and that's it. Store results to stack so that we can load take user scalar instructions. Alright, this is all unsatisfying, but I guess let's look at this. Especially since... Alright, the performance is the same, of course, but I believe... I don't think I'm using student in other parts of the library, but it's probably fine. I was planning to start doing this anyway. So I think right now we don't need SSE41 anymore. I believe so. Yeah, okay. Alright, fine. I'm kind of disappointed. Oh, the code now runs a tiny bit slower. I think when we were using SSE41, the compiler was doing some optimizations on some parts of the code. Anyway, so I'm a bit disappointed that there wasn't like a better solution than just doing the same thing that we did before. But that's sometimes the case with SIMD. It's just you do what you do the only thing that works. I would like to check Microsoft's performance. Microsoft Visual Studio performance. Because I'm not sure that it actually is good. Have to compile this again, and then we are just gonna finish this because I'm getting like really tired at this point. Right, so Microsoft's compiler is slightly weird because it doesn't define SSE2 on 64-bit, I guess. Which doesn't necessarily make a whole lot of sense. Is it not Exponential? Which intrinsic header is this? Oh, it's EMM. Alright, so now once we fix that, Microsoft's compiler runs at 2.3. And I think the reason is rotates. So Microsoft has an intrinsic called ROT-L or something like this. Yeah, ROT-L64. And now, oh, Microsoft's compiler runs even faster now at like 3 GB a second. Interesting. Cool. It's interesting that Microsoft consistently on this test seems to outperform Clang, which, you know, you don't see very. Oh, well, it's not Clang, it's GCC. Is it GCC? What have we been using? No, we were using Clang. Hopefully the code compiles with GCC now that we don't use the intrinsic. Yeah. GCC runs a touch faster, perhaps. Alright, so I think that about does it for this code. I was like hoping that there would be a better way to do this, but I guess there is not. It's just no better way to do this, which is probably fine. Alright, I'm tired. We did 2 things. I was hoping we would do 3 things, but we did 2 things, all the same. Maybe I'll finish this myself in like an hour, we'll see. Alright. But I think it's time to end the stream, because I definitely need a break from this stuff. I'm gonna go play Beat Saber or something. And then maybe I'll finish this, or maybe I will finish this at some point later. The function we did not get to is actually like much more straightforward. The function we didn't get to is actually like really boring, because it's the same thing that we've been doing, just like more of it. I'm just gonna copy and paste this, and it's gonna be easier to like describe in the spec format. So the function we did not get to, the 2 functions we did not get to that are actually like very similar, I'm just gonna go copy, paste, replace SIMD bits, replace the integer conversion instructions, done. And then just write up a description here, which is actually straightforward, because you don't have to talk about. The encoding is similar to Quaternion encoding in a bit, but you don't have to talk about maximum components and things like that. It's like a simplified version, more straightforward version, I think. Yeah, so that's gonna be zero. Alright. I'm exhausted. Thank you for watching the stream. Sorry the stream had problems. I actually have no idea what will happen with YouTube encoding, YouTube like video for this, because we had really horrible problems in the middle of the stream with internet, and I had to cut the router and reboot that. So maybe that, like, I just don't know what happened. It's going to be interesting to see what happened with the stream. All right, I'm gonna go have a bite, you know, rest a bit, and maybe finish this stuff. I don't really have the energy for questions, so even if you guys have questions, I'm sorry. The video will be up on YouTube. Thank you all, and bye.